Hello everyone, let's discuss the concept of magnetic flux. So what is magnetic flux? Which is nothing but measurement of total magnetic field which passes through given area. Measurement of magnetic field which passes through given area, which is nothing but, let us consider two poles. This is south pole, this is north pole. So for better understanding, consider these two poles, and between these two poles obviously we are having magnetic field lines. We are having magnetic field lines. These are the magnetic field lines between these two poles, south and north pole. So let us consider a conductor. Let us consider a conductor. This is the placement of conductor. This is the placement of conductor. What is the definition of magnetic flux? Measurement of magnetic field which passes through given area. So this is the conductor. The length of the conductor is, let us say, L. So the measurement of magnetic field, these are nothing but magnetic field lines. The measurement of magnetic field which passes through given area. So these are from south pole to north pole. So we have to measure the flux which covers the area of that magnetic field, which is nothing but the area of the conductor. So the magnetic field lines which covers the particular area of the conductor that they are gone through. This is the area. So in this area only we are having magnetic flux. So what about this area which doesn't cover the magnetic flux lines? Therefore phi which is equals to 0. Therefore phi which is equals to 0. So in this region phi is equals to 0, like that. In this region phi which is equals to 0. Then what about this region from here to here? Phi which is equals to finite value. Finite value. So this is nothing but magnetic flux, which is nothing but measurement of magnetic field which passes through given area. Means which describes the effect of magnetic force on occupying area, which is nothing but we are going to experience some magnetic force on area that they are occupying. So this is about the introduction of magnetic flux. So let us consider these two diagrams. So if we use the field line picture, so field line picture is nothing but what? Let us say this is south pole, this is north pole, south, north. So these are nothing but magnetic field lines. These are nothing but magnetic field lines which covers the area of the conductor. Let us say this is the conductor. This is the different orientation of the conductor, like that. In this picture also, this is the different orientation of the conductor. So if we use the field line picture of magnetic field, then every field line which is passing through the given area contributes some magnetic flux, right? So if you consider this is the conductor, so this field line should passes through this conductor, right? So from here to here, obviously from here to here, phi which is equals to 0, from this position to this position, phi which is equals to finite value of flux, like that from this position to this position, phi is equals to 0, right? Like that from here to here there is no flux cutting, obviously 0, from this position to this position, phi which is equals to finite value, coming to from this position to this which is equals to 0, right? Because there is no flux cutting. Only there is a flux cutting when there is a conductor which is present between south and north pole, or which is present between two poles, whenever we have magnetic field lines through that conductor, then only we are having some flux. And this is the angle, this is nothing but a glancing angle, we will discuss, this is theta. Okay, so the angle at which the field line intersects the area is also very important. So here the conductor which is placed, the surface is little bit inclined between these two poles, that's why we are having some angle. But coming to this, the surface is obviously 90 degrees, the surface which is perpendicular to this magnetic field lines, right? Therefore theta which is equals to 0, theta which is equals to 0. So this is the angle, this is the angle, but the surface is perpendicular, then theta is equals to 0. But coming to this, there is an inclination of the conductor to the magnetic field lines, obviously between this surface of the conductor and field lines, obviously we are having some angle, that angle is nothing but glancing angle. So a field line passing through at a glancing angle will only contributes a small component of field to the magnetic flux. This is very important point. So the total flux is depends on the glancing angle, right? So when calculating the magnetic flux, we include only the component of magnetic field vector which is normal to our test area. So if we choose a simple flat surface with area, so this is the simple flat surface of the area A as our test, and there is an angle theta between the normal to the surface and a magnetic field vector B. So we have a conductor which is having a area A, and we have the field lines, and they are having a density which is nothing but magnetic flux density which is nothing but B. So because of this two objects, obviously we are going to get the magnetic flux which is explained by phi which is equals to B A cos theta. Amount of magnetic flux phi which is equals to B A cos theta. So from this first diagram, what is theta? Obviously theta which is equals to finite angle, right? Finite angle from this. But from this diagram theta which is equals to what? Theta which is equals to 0. Obviously the surface of the conductor is placed exactly 90 degrees to this field lines. Then this is 90 degrees. The surface should be 90 degrees to the field lines. But what about this, which is the area, sorry, the angle between this surface and this surface is nothing but 0 degrees. Theta which is equals to 0 degrees from this diagram. So from this, phi which is equals to what? Magnetic flux. From this first case, finite value, but which is less than the maximum value, but which is less than the phi max. Which is less than phi max. But in this case, theta, there is no inclination between the surface of the conductor and the two pole placement. Therefore, the magnetic flux phi which is equals to BA cos theta. So cos 0 is nothing but 1. Obviously, we are going to get BA which is nothing but phi max. So we are going to get maximum flux in this region. So in this case, the flux which is less than the maximum flux, but coming to this case, we are going to get the maximum flux. So based upon the theta, we are going to get the different values of magnetic flux. So the glancing angle is very much important to get the magnitude of magnetic flux. It totally depends upon the orientation of the conductor between the magnetic field lines, right? So in the case that the surface is perpendicular to the field, then the angle is 0, and we are going to get the magnetic flux which is nothing but maximum flux, right? So because the magnetic flux is just a way of expressing the magnetic field in a given area. So this is the expressing the magnetic field in a given area. So it can be measured. The magnetic flux can be measured by using a magnetometer. So this is the meter which is required to calculate the magnetic flux, right? This is about the concept of magnetic flux, and in addition with that magnetic flux, we are going to discuss the concept of magnetic flux density. This is very much important. B. So a related term that you may come across the magnetic flux density B. So this is the measured quantity in Weber per meter square, because we are dealing with respect to area of the conductor, right? So this is the unit of the magnetic flux. Sorry, you can write unit of the magnetic flux, unit of Webers. So in addition with that, we are going to discuss the magnetic flux density, and this is the unit Weber per meter square, because we are dealing the analysis with respect to per unit area. Because we are dividing the flux by area, we could also directly stated that units of flux density in Tesla, Weber per meter square or Tesla. So which is nothing but magnetic flux density, magnetic flux density. So let us say this is the magnetic core. This is the magnetic core, and this is the magnetic flux through that core, and this is the orientation. So within the particular area we have to, this is nothing but area, cross sectional area. So we are going to calculate B, which is equals to the amount of flux per cross sectional area is nothing but Weber per meter square. This is magnetic flux density or Tesla. This is the very small concept of magnetic flux density. So in addition with that, we have to discuss magnetic field strength. Magnetic which is nothing but H, right? We are having north and south poles, which is nothing but H, which is equals to mmf by length of the conductor, which is nothing but magnetomotive force. We will discuss what is magnetomotive force in the next class, by length of the conductor. So which is nothing but number of turns and current through the turns by length, which is nothing but current unit is ampere and turns ampere turns per meter, right? Ampere turns per meter. This is the unit of magnetic field strength, which is nothing but mmf per unit length. mmf per unit length. How much voltage that we are going to get per unit length is nothing but magnetic field strength. So then the question comes here, why we need magnetic flux. We will discuss what is magnetomotive force in the next class. Then why we need magnetic flux? Obviously to get how much EMF induced in a particular machine. So because of that magnetic flux only we are going to get that how much EMF that is going to induced in a particular machine. We all know that, which is nothing but rate of change of flux linkages, which is equals to minus n d phi by dt, right? Flux linkage is nothing but n into, or you can write this minus n indicates the direction of induced EMF, which is explained by Lenz's law, or you can write d n phi by dt, rate of change of flux linkages. So from this minus n d phi by dt, that is the value of EMF. So because of this EMF, that's why we need magnetic flux to get how much EMF induced in a particular machine. That's why we need this EMF. So I will explain in detail how we are getting this EMF from the Faraday's law of electromagnetic induction. So this is the concept of magnetic flux and magnetic flux density and magnetic field strength. What is magnetic flux? Measurement of magnetic field which passes through given area. So this is the example for that explanation. Thank you.